And the approach to doing that is known as reinforcement learning. This is learning on the job, learning through experience. So the approach we use here is a method called temporal difference learning. My time constraint means I can't give you a very satisfying definition of what this is, but I'll try and give you a very high-level overview of what's happening. So we keep the same structure that we had with our supervised learning. We keep our bids to describe the state, we keep our neural network, and we keep our probability function, except we now just do a cheeky change of name of this function rather than calling it the probability that the human would pick the red stage in this situation. We just call it the probability that that's the right stage to pick. And we let that control the junction. And as we're controlling the junction, we make decisions. As we make decisions, we receive feedback. Excuse me. If the feedback tells us we've made a good decision in that particular state, we can, actually I'll just click this, this plays a little animation. We can take the probability surface for that decision, or that state for that stage decision in that state, and we can just tweak it upwards slightly, increase the probability a little bit. Conversely, if we think the decision's bad, we can tweak it downwards slightly. Just a very small amount. But then as these decisions add up and accrue over thousands and thousands of decisions over the course of a test, combinations of states and decisions that consistently return high reward or high feedback will build up higher probability of being picked in the future. And there's a slight problem here that maybe you may have already spotted. Under the supervised learning situation that I described, we had a very deterministic way of picking which stage. We always picked the stage with the highest probability. If we did that here under reinforcement learning, we would never really learn anything new. You can't learn if the decision is a good or bad if you never try it out. So you need to have a situation where you try out new decisions. So we changed the way we make decisions, and it's very simple. If we go back to our original idea, our two bids defining our bid space and our two stages with their corresponding probability surfaces, if we take a new point, a new state, defined by this green line here, that has two probabilities. The probability that blue stage is the right stage to pick, which is 75% here. Probability that red stage is the right stage, which is 25%. And so we can just roll an imaginary two-sided dice, which has a 75% chance of coming up blue, 25% chance of coming up red, and pick it that way. So to be clear, once every 4 times or so this state's encountered, we'll pick the red stage. And if we get positive feedback, that red stage will have its probability of being picked in the future increased. Okay, so here's a result from a training session. This is pretty early days for applying the reinforcement learning. This training session is done on the simple T-junction I showed you before. We start by initializing our probability surfaces randomly, or nearly randomly, so they're quite flat. So essentially, when we start off running the test, the junction controller is just changing the lights at random. So as you might expect, it doesn't do very well. This is a very low demand as well, just to make it easy. So you can see as the test starts, the delay shoots up because it's just making random decisions. But pretty quickly, it starts to work out what's happening and starts to learn. And this learning you can see reflected in the reduction in delay as the test progresses. This is an 18-hour test, training session. We repeated this training session over and over, constantly increasing the level of demand so that we built up a complete mapping of our bid space to control the simple T-junction using neural network trained by reinforcement learning. And then, of course, we can compare that to our neural network trained by a human. And this is the result. Again, we've used variable demand going into a 4-hour test on the simple T-junction. And you can see the peaks in demand, and you can see that our reinforcement-trained neural network matches the performance pretty much of our human-trained neural network over most of the test. And the point where it breaks down is this point of highest demand, this point where the junction's at its busiest. The reinforcement learning, this is where the human learning still has the edge. Now, I mean, it's a bit, the reasons for this are a little bit complex, but I mean, these are early days in these tests, and I think this is maybe something that can be dealt with in the future. So we'll see over time, maybe, you know, UTSG next year, you might find out how reinforcement learning has progressed. So I just want to conclude by making some comments about sort of the applicability of this to the real world. How would you go about applying this in the real world? Well, the first thing is to mention that all the tests we've done here have been based on simulation, but that the learning strategies that I've discussed are completely data agnostic, okay? So they can quite happily be trained on data on real-world data. And if that sounds like I'm saying I want to put Nick Hounsell in a cherry picker above a real junction with some buttons, you're absolutely right. I would love to do that. I think that would be a really interesting experiment. We'll give you a flask of tea, Nick, to take it with you. It'll be fine. The second thing to say is that what we did here with the reinforcement learning, where we initialized randomly and just let it learn, you obviously couldn't apply that in the real world, because I don't think you'd find a local authority that would be very happy, even for a few hours, to let you change the lights randomly on one of their junctions. But you can combine the methods. So you can train up using a human and then apply the reinforcement learning, or you can train up on reinforcement learning offline, on simulation, and then transform it. But I mean, is there really any point in this when we see that our reinforcement learning didn't actually beat the human learning? Well, you know, maybe it will in the future. You know, there's still work to be done there. But there's still an advantage for it. And that is in the situation, if you have a control strategy, a control algorithm for your junction that works really well, that's really optimized for today, do you know it's going to be optimized in 2010 or 2015 or 2020 when maybe driver styles change, maybe there's more electric vehicles, maybe someone's built a new road nearby? If you have the reinforcement learning running in the background, then if the junction starts to drop, if the performance of this controller starts to drop due to changes outside your control, then these can be recognized and corrected for, and your junction can learn and improve for itself over time. Okay, so that's the end of my talk. I just want to give you a quote just to finish up. This time of year, whenever the new year rolls around, newspapers tend to roll out these crystal ball gazing articles. The Observer's contribution this year was an article called 20 Predictions for the Next 25 Years. This was published on Sunday. Number 10 was gaming, meaning in this context, computer gaming. We'll play games to solve problems. Now, given that the Observer have given this a 25-year timescale, I'm quite pleased to have presented an example at a conference only 4 days later. I don't know if I'm ahead of the game or if the Observer are behind. I think probably the latter, but at least we're topical. Thank you very much.
That's great, Nick. Have we got any questions for Simon?
You're basing the performance of the algorithms based on the delay that you experience at the junctions. Yeah. But looking at Margaret here, there's no reason why you couldn't try and optimise it based on the emissions or the air quality concentrations that we're accruing. So you could actually choose which parameter you're trying to optimise for. Okay, well, I mean, I would hope that delay would be pretty strongly correlated with emissions. But certainly you could use that as a measure of your performance as well. I mean, the problem here is especially if you take the example of the human training, I mean, I'm not really sure. I mean, I've asked everybody who plays this game, and I've never managed to get a straight answer. People don't really know how they're making their decisions. It's quite interesting. But I'm pretty sure they're not thinking, must minimize CO2, must minimize CO2. So that's an interesting point. But again, with the reinforcement learning, you could build that into your feedback signal if you had that data. Quite how you would get that and feed that in, that's an engineering problem, we'll say.
Ben, you've got a question? Yeah.
Well, first of all, I would like to congratulate you on your choice of humans who have produced excellent baselines for your experiments. That actually is a serious comment, because I believe that in the past humans have not performed particularly well in this area. On the two extremes, you showed performance for the mover method. Mm-hmm. And I'd like to ask, as one of two questions, do you have access to the mover algorithm? And if you do, where can I find access, please? And the second is, have you considered using some objective method, say dynamic programming, which we know is impractical, but some objective method in order to find a baseline beyond which further progress is not possible, so that you can see on some scale how well your method really is doing.
Okay, I'll start with your second question, because the answer is easy, because it's no. But that's a really interesting suggestion. It's something we'll certainly consider. Your first question, MOVA is a black box to us. We don't know the MOVA algorithm. What we do have is an API designed by TRL. And in fact, that junction, the simple junction we showed, is their exemplar junction that they provide with the MOVA API. So we use that one just so we could not be accused of fudging our poor configuration of MOVA or something like that. So that's your answer to that question.
Any other questions? At the back with us.
Mohammed Quddus, Labra University. Thank you very much for a very interesting presentation. I'd like to know either, have you considered to integrate data from GPS with data that you can gather from Wi-Fi access points so that you have the coverage in terms of GPS denied environments?
Yeah, I should clarify actually what I mean when I say GPS. Actually, I'm using the term GPS because that's something everybody's familiar with. Of course, we don't have real GPS. This is a simulation. So I should tell you how we simulate GPS. That's probably the best answer to that question. So obviously, Paramix reports a perfect position for vehicles. We realize that this is unrealistic. So we add Gaussian noise, and we can choose the standard deviation or the variance of the noise that we add. So maybe we can just add a small amount of variance, and this might be a reasonable simulation of an accurate localization system that uses maybe GPS combined with something else. Or maybe we could have something 5-10 meters, which would maybe be more representative of GPS alone. So it's not a case of we're actually accurately simulating GPS or inertial measurement or Wi-Fi localization. We're just taking position and we're adding noise. Obviously, different amounts of noise can be in some way representative of different localization systems. And in fact, we've done a paper on that, on how the performance varies with variation in positioning accuracy, and also variation in the number of vehicles equipped with probes, because obviously we don't anticipate a scenario which will immediately have 100% of vehicles equipped with probes. I can't remember which journal that's gone to, but maybe I'll let you know later on.
Good. There's one at the back there.
Hi, Jens Kaparias, Imperial College London. Just a question. You used neural networks. Have you considered any other machine learning methods?
Actually, so we just tried to start simply and build up. So the first thing we deployed was a logistic regression, and that worked quite well on the simple junction, but broke down later on. Then we sort of went up to a neural network, if you like, in the hierarchy of complexity, and that's actually performed really well so far. We have briefly considered looking at kernel methods, but we haven't gone into this yet. This is maybe something to the future, but the neural networks seem to be performing quite well for us at the moment. And also, actually, I wanted to put this slide in my talk, but I didn't get around to it. The inspiration for this work came in quite a large part from, when we realized this was an artificial intelligence problem, we tried to look for other similar problems in the literature. And computer backgammon was what we came up with. And it might not be immediately obvious to you, but there's actually some striking similarities between backgammon and signalized junction control. And there's been some really excellent work done by this man, Gerald Tesoro, an engineer at IBM, who trained his computer to play backgammon in almost exactly the same way I've described here. First, he developed NeuroGammon, which is a neural network which learned how to play backgammon from human grandmaster backgammon players. And then he designed another algorithm called TD-gammon, which learned by temporal difference reinforcement learning with his backgammon program playing against itself. And that's why I have a bit of confidence that maybe the reinforcement learning will come through, because in this case, the temporal difference gammon ended up outperforming his original NeuroGammon quite significantly. But I mean, that doesn't mean it's necessarily going to work for us, because the problem's similar, but they're not identical. But yeah, I hope that answers your question.